What's going on, guys? Welcome back to the channel. Stefan here from AppStuff, and we have a super exciting video for you here today. We are going to be going over the S.O.L.I.D architecture principles with Swift. I've gotten a ton of requests for this video, so I decided to finally make it for you guys. So let's go ahead and get started. By the end of this video, guys, what are you going to achieve? You're going to understand S.O.L.I.D architecture first and foremost. You're going to implement a bunch of code examples of each principle. And then we are going to show you guys where you can go after this to actually apply these principles with building mobile apps, right? So we're going to go over code examples in this video, and then we'll show you where to go to actually apply these concepts in building a real life mobile application. So guys, let's go ahead and get started with an overview of S.O.L.I.D and what it is. So it's basically 5 code architecture principles that, when applied together, intend to make it more likely that a programmer will create a system that is easy to maintain and extend over time. So let's do a deeper dive into what each principle is here, guys, and then we're going to get started with the code. So we have S, which stands for Single Responsibility Principle, or SRP. O, which is the Open Close Principle. Then we have Liskov Substitution, Interface Segregation, and Dependency Inversion. So we are going to be going over an example of each one of these principles, guys, and how it all sort of fits together to help you build a reliable system in terms of how your code is architected and structured. So let's go ahead and get started with the code now. All right, guys, with Xcode opened up, what you're going to want to do is create a blank playground. So to do that, just go to Xcode and you're going to hit File, New, and select Playground and just create a blank playground, and then go ahead and write these notes out. We are going to start off with the single responsibility principle, and we have these notes here denoting what it does. So to get started, a class should only be responsible for one thing. That is the foundation of the single responsibility principle, guys. And if you're wondering really quickly what all these other modules are, guys, memory management, higher order functions, generics, and all that stuff, that is the intermediate and advanced fundamentals course on our website. So if you head over to stefancodes.com, the link is in the description. You guys can go and check out the intermediate and advanced fundamentals course. And if you guys want to implement S.O.L.I.D architecture principles in an actual app, go ahead and take the Swift networking masterclass. We build an awesome cryptocurrency app here, and we follow all of the S.O.L.I.D architecture principles there. And it's a great way to go over how to implement each one of the S.O.L.I.D principles with building a real life application, guys. But let's go ahead and get started now. So guys, basically what we are going to do for each example is show the bad way of implementing it and then implement the S.O.L.I.D way to show you guys how that can help us out with making our code more extendable, maintainable, and reusable. So we are going to start this example out by creating 2 data structures, guys. So just follow along with me here. We're going to create a product structure, and it's just going to have a price. And then we are going to create an invoice structure. And I'm just going to copy and paste this, guys. You can pause the video and type this out if you like. And this is what the invoice structure is going to look like. It's going to have an array of products associated with it. An invoice is going to have an ID and some discount percentage we can apply if we want. It's going to have a computed property to help us get the total of all of the products, and that incorporates the discount as well. Pretty standard. And then a function to print our invoice and then save our invoice, right? So here we could save our invoice locally or to a database. So this code might look fine to most people, right? It's like pretty standard, not a super complicated object here, but this actually violates the single responsibility principle. And that is because this invoice structure is responsible for multiple things, right? So we have it responsible for getting a total, we have it responsible for printing out an invoice, and then we also have a persistence responsibility where this structure is also responsible for saving our invoice, whether it be to core data, file storage, or some sort of database like Firebase or AWS, right? So we only want our class to be responsible for one thing. So I'm going to go over how we can modify this invoice structure to make it so that it adheres to this single responsibility principle, guys, and we'll go over why that is a better code structure than what we see here. But before we do that, guys, let's take a look at what it would mean to actually create some products and an invoice and like maybe run this printing function just so we can get an idea of what this code is actually doing. So we have some products, we have an invoice, we pass along those products in the initialization. We say that we're getting a 20% discount on each product, and then we want to print out our invoice, right? So that might look something like this. So we have our invoice ID, our total cost, and our discount, right? So back to the single responsibility principle, guys, we notice here that this function is responsible for printing our invoice, right? But we said that we only wanted our class to be responsible for one thing. So how do we solve this problem using the S.O.L.I.D principles? SRP in particular. Well, what we want to do is extract this functionality into another class. So what I can do, guys, is go ahead and create another struct and maybe call it invoice printer. And we want to basically just take this function and move it into this structure, right? So this class will have a single responsibility, or struct will have a single responsibility of printing our invoice. And we're going to do the same thing for this. The only problem we're faced with is how do we actually get this invoice data? Well, we're just going to declare that an invoice printer has to be injected or initialized with an invoice, right? So now we can say, hey, go ahead and print invoice.id, print invoice.total, and print invoice.discount percentage. Oops. Right. Okay. So now, guys, we could completely remove this function. I'm going to comment it out. And if we wanted to print our invoice, we could then just go ahead and say, let printer equal invoice printer. And we could pass in our invoice, and we could say printer.print invoice. Just like that, right? So let's go ahead and run that. And we'll notice it accomplishes exactly the same thing, right? We see the exact same print statements, and we have extracted this piece of functionality into its own class, adhering to the single responsibility principle, right? So we're removing complexity from our invoice class, we're creating a separate one, and it does the same thing. And this is more scalable, maintainable, and readable code here, guys. And we could do the same thing for our invoice persistence. So let's go ahead and do that. Let me go ahead and say struct invoice persistence. And we're going to inject this with an invoice as well. And we can just have this function here, save invoice, boom. And guys, this would just execute whatever functionality you need to actually save your invoice, right? And then down here, we could say let persistence equal invoice persistence, invoice, pass along our invoice, and we could say persistence dot save invoice. So that completely removes the need for us to have this function here as well, right? So this is the essence of the single responsibility principle, guys. We have really cleaned up our class so that it only is responsible for one thing, getting the total of our invoice. And then we extracted the other functionality that was originally part of that invoice class into two separate structures, right? And we noticed that each one of these things is responsible for its own thing. So there is a drawback here of this sort of system and setup that I don't particularly like. So I'm going to show you guys a better way and more scalable way of implementing this SRP. So guys, let's imagine that we wanted to create another invoice here. So let's imagine I wanted to say let invoice 2 equal invoice, and it's just my products with no discount, right? If I wanted to do this same stuff, I would have to create another printer and another persistence object, right? So I would have to say, let printer 2 equal, and we would have to say, invoice 2, and the same for persistence. And this to me isn't very scalable, right? You guys could maybe make this a little bit different where you made this a variable and you could then set the variable accordingly, like printer.invoice equals invoice 2 or something like that. But I don't particularly like that. I think what's a better option here is to keep these functions on the invoice class and simply create a printer in the print invoice function, right? So what you would do is say in the print invoice function, you would say let printer equal invoice printer, and you would pass in self, which in this case refers to invoice, and then you would say printer.print invoice. And you could do the same thing here. And I personally believe this is just a significantly more scalable solution. This class is still only responsible for one thing in terms of getting the total. It has a print function and it has a save invoice function, but all of the implementation logic and functionality is extracted to other classes, guys. So I personally think this is a better option. So let me just go ahead and do this guy as well. We could say let persistence equal invoice persistence and pass along our invoice, and say persistence.saveInvoice. And this would actually be self as well. So this way, guys, what you could now do is you wouldn't have to create these objects every time you wanted to use them. You could simply say invoice.printInvoice and invoice2.printInvoice, right? And let's go ahead and run this code and see what that gives us back. Oops. We can delete that code. And guys, we notice that we get back two separate invoices. This is invoice 1 and invoice 2, different totals, different discount percentages, blah, blah, blah. And I think this is honestly a much cleaner implementation. So that is my spin on the single responsibility principle, guys. If you have disagreements with that or a better way of accomplishing that, please feel free to drop that in the comments. This stuff is always open for discussion. This is the essence of high-level programming. There's not necessarily one right way of doing things. There are a bunch of different ways, and each way has its own potential drawbacks and advantages. So that's it for SRP, guys. Let's go ahead and move on to the open-closed principle. So I have some notes in here, guys. Let's go over them before we jump into a code example. We see that software entities like classes, modules, functions, structs, etc. should be open for extension, but closed for modification. So in other words, we can add additional functionality without touching the existing code of an object. So you guys might have recognized this before in something like this. So you might see an extension on a particular value or data type that Swift provides to us, like integer or string or double or whatever. And then we can add functionality to that data type by extending it like this. And then we would be able to implement it like this. This adheres to the open-close principle, or OCP, because we can't directly modify the integer data type, right? Or strings or doubles or whatever. We get those from Swift and we can't touch them. We can, however, extend them, and that is the foundation of OCP. So I'm going to just go ahead and delete this, guys. If you want to learn more about extensions and how they're used, check out our Swift Fundamentals, Intermediate, and Advanced Fundamentals course. We have a whole module on that here. But let's keep going with this example. We are going to grab this invoice persistence structure and use that to go over how we can adhere to the open-close principle. So guys, let's go ahead and call this invoice persistence OCP. And let's imagine that we wanted to add functionality to this struct or class, guys, to be able to save invoices with different methods. Like, let's imagine we wanted to save to core data or save to cloud storage, whatever it may be, right? Let's go ahead and take a look at what that would look like. So I would have to, let's go ahead and just replace this function with two other ones, like save to core data, save to database. And then if we added some different database to our application, I would then have to go and add another function to this class, right? And this is violating the OCP, or open-close principle, because we are modifying this object to add functionality to it. We want to make it extendable, or get the functionality we want by creating extensions of this class. And I don't just mean going extension, invoice persistence OCP, and then creating more functions, right? Like, technically you could do that and maybe consider yourself being in, adherence or conformance to the open-close principle, but there is a better way of doing it. And we are going to accomplish that through a protocol, guys. So we're going to create like an abstraction here using a protocol, and we're going to call this invoice persistable. And what we're going to do is just add a function here called save, and this is going to save an invoice. And what we're going to do is create separate components for each different type of our invoice persistence. So this is pretty similar to the SRP, the single responsibility principle. Let's go ahead and see how we can implement this protocol to follow both the SRP and the OCP. So I would go ahead and create another structure, guys, for core data persistence. And it would conform to that protocol, invoice persistable. Right there. And I would implement this function by saying fix, okay, I know I need to save an invoice. And let's go ahead and just add a print statement to this, right? Print save invoice to core data. And now I have a separate structure that is responsible for my core data persistence, and it conforms to this protocol. I'm going to do the same exact thing for my database persistence, guys. So let's go ahead in here and just paste that bad boy right there. So now, guys, I no longer need to add functionality to this base class, right? What I would do if I wanted to add additional persistence layers or methods is just follow this pattern, right? Create another structure, conform to the invoice persistable protocol, and then I could then implement that save function however I wanted to, right? So let's go over how we can now modify this structure to take advantage of this setup. So instead, guys, let's just go ahead and literally delete all this code, right? We don't need it anymore. What we're going to do is say, hey, just initialize this with that protocol type, invoice persistable. And then I'm going to have a single function on here called save invoice, which is an invoice. And we are going to say persistence.save and pass along that invoice, right? So the implementation of this would now look like this, guys. We could say let core data persistence equal core data persistence. And we would then say let persistence OCP equal invoice persistence OCP and pass along core data persistence. And then we could simply say persistence OCP.save and pass along that invoice that we created back up at the top. And let's go ahead and print that or run that, guys. And we will see that we're saving that invoice to core data, right? And then, guys, if I changed this or I created a, database persistence, just like that, I could pass this along here and save that way. So sorry, let's go ahead and run that and check it out. And guys, you notice that it's now saving it to Firestore. So we have made this structure significantly more abstract, and we adhere to this open-close principle. We're adding functionality to this. We simply extend it through use of this protocol and creating separate structures. So this is like a combination of both SRP and OCP, guys. So we can really start to see how these concepts relate to each other to help us write more scalable, reusable, and maintainable code. So guys, let's go ahead and hop into the next example, which is going to be the Liskov Substitution principle. I know that sounds super intimidating, but it's really not that bad. Let's just go ahead and get started with it now. So our notes, right? A derived or child class or structures must be substitutable for their base or parent classes. So guys, essentially, let's just go ahead and do an example to explain this, right? I'm going to create this enum, which is going to be like simulate an API error, right? So we could have a couple different API errors. You guys notice that this enum conforms to this error protocol type, right? And then I'm going to create something like a mock user service, something that you might use in testing, or you guys could, imagine this is a production service or something, but basically it's just going to throw an error right away, right? So guys, what this is doing is we are substituting the base class of error for this custom type. So this is essentially what the Liskov substitution principle is. Derived or child classes or structures, in this case it's an enum, must be substitutable for their base or parent classes. So this is using some of the async await stuff with Swift, guys. That is covered in extreme depth and detail in the Swift networking masterclass. So make sure you guys go ahead and check that out if this is confusing to you. But basically, this is just stating that this function can throw an error, right? You guys will notice that I could change this out to like a URL error, right? And say like, I don't know, bad URL, right? And this is, if we go ahead and hold down Option and take a look at this type, this structure URL error is like conforming to NS error and also conforms to the error protocol, right? So guys, this function can throw either that error type or the custom error type that we created, but essentially the base class behind all of them is error or NS error, whichever one it is. And we can substitute those things for their parent classes, right? This is the child class or structure, and I can throw any type of error I want. API error dot invalid response, right? And so let's go ahead and see an example of this. We could say let mock user service equal mock user service. And we could say task try await mock user service dot fetch user, and let's see what we get back. So let's go ahead and run that, and we notice here that we get an invalid response, guys. So once again, the child class is substitutable for the base or parent class. When I want to throw an error, I can use a custom error structure. So that's the Liskov substitution principle. That one was short and sweet. Let's go ahead and jump into the next one, guys, which is going to be the interface segregation principle. This one is super cool. So we're moving right along here, guys. We are going to say that we don't want to force any client to implement an interface which is irrelevant to them. So another simple example we're going to go through here, guys, is we're going to have a protocol here, and this is going to be something like a gesture protocol, right? So anything that conforms to this, something like a button, would implement these functions: tapping, double tapping, and long pressing, right? So let's imagine I had some sort of struct, which is like a super button that can do all of those things. So it's going to conform to the gesture protocol, and then I'm going to implement what I want to happen when each one of these things gets executed. When I tap on it, it does this. When I double tap, it does that. When I long press, it does that, right? So pretty straightforward. But let's imagine now that I create another button, something like a double tap button, and also make that conform to the gesture protocol. But the only thing this button needs to do is have a double tap handler, right? So guys, what we would look at here is say, I only need this guy. But this is in violation of the interface segregation principle because we're conforming to this gesture protocol and we don't need these functions. So sometimes with bad code, you guys will see protocols that literally just have blank functions where they're not doing anything. And then this is the only implementation: print, debug, double tap, or something, right? So once again, guys, this violates the interface segregation principle because this double tap button is implementing functions that it doesn't care about or doesn't need, right? So do not force any client to implement an interface which is irrelevant to them. So what we're going to do is basically just divide this gesture protocol up into individual protocols to make sure that we adhere to this principle. So really quickly, guys, I'm just going to go ahead and paste these bad boys in here. They're super simple to type out. We're going to have a single tap protocol, a double tap protocol, and a long press protocol, right? So instead of this gesture protocol, right, what we would do is just go ahead here and say single tap, double tap, and long press protocol. So this guy conforms to all three, and then this guy could simply just conform to our double tap protocol. And be able to clean up our code, guys, and remove these unnecessary or unused functions. So this is how we conform to or adhere to the interface segregation principles, guys. Make sure you're not forcing any client or thing that like an implementer or adopter of a protocol to implement interfaces which are irrelevant to them. And this is how you solve that problem. You just create individual protocols or interfaces to help you like modularize your conformance here or your abstraction layers. So next up, guys, we are going to look at the final principle, which is going to be the dependency inversion principle. So let me go ahead and grab my notes here. So let's do a quick breakdown of this before we jump into an example with the code, guys. We see that high-level modules should not depend on low-level modules, but should depend on abstraction. If a high-level module imports any low-level module, then the code becomes tightly coupled, and it then becomes harder to scale and maintain. We want our code to be loosely coupled, more generic, and abstracted, right? So this could also lead to changes in one class breaking another class. So let's go ahead and jump into an example, guys. Let's imagine we were building an app that could process payments or integrating a payment feature into our app with a bunch of different payment methods. So I'm going to go ahead and just copy and paste some code in here. Let's imagine we had some payment struct, right? We can have a debit card payment, a Stripe payment, or an Apple Pay payment. So here's what this would look like with those individual structures. We have all of this stuff here: debit card, Stripe, and Apple Pay payment. So let's go ahead and take a look at what it would look like to initialize this payment structure. Let's imagine we wanted to execute a debit card payment, like the user selected that option, right? So let's say let payment method equal debit card payment, let payment equal payment, and we would have to then initialize it with all of these things, right? And I would have to say payment method, and then I would have to declare Stripe payment as nil and Apple Pay payment as nil. So this doesn't follow our dependency inversion principle, guys, right? We have a high-level module here, which is a payment that depends on a bunch of low-level modules, like the individual payment methods. And then to execute this, guys, I would have to do something like payment dot debit card payment dot execute for like $100 or something, right? And then we get this really nasty optional chaining, and I don't exactly know which payment method is non-nil, right? Like that could be really frustrating for me to figure out. Like at some point in the code, someone could accidentally say payment.Stripepayment.execute and do that for $100. But I didn't supply this payment structure with a Stripe payment. I supplied it with a debit card payment. And there's no way of really knowing that without doing like a bunch of logic checks with like if-lets or guard-let statements or whatever. So this is really messy code. This isn't super scalable. And we have this problem of a high-level module depending on a bunch of low-level modules. So we want to instead depend on abstraction, guys. So we are once again going to implement the use of a protocol. So I'm going to go ahead up at the top and say protocol, and we're going to say payment method. And we're just going to have this one function that all three of these things are doing, right? They're all executing a payment, and they're just going to do it differently, right? This is going to go to Stripe. This is going to go through Apple Pay, blah, blah, blah. But all we care about is the amount with a double, and then each one of these functions can adopt this protocol and implement it as they need to, right? So I would go here and say payment method, and payment method. So now we have an abstraction, right, guys? So instead of having this nasty struct with a bunch of optional payment types, what I could do is go ahead and create a new one. We can call this payment DIP for dependency inversion principle, and we could just inject that protocol. Payment, which is a payment method, func make payment for a particular amount, which is a double, and then I could say payment method payment dot execute that amount, right, guys? So this is significantly better code than what we had up here. And guys, to implement this, let's go ahead and say like maybe let Stripe equal Stripe payment, and we would then go let payment dependency inversion principle equal payment DIP and pass in that Stripe guy, and then we would just say payment DIP dot make payment for like $200 or something like that, right? So this is a much cleaner implementation where our high level module, which is this payment DIP, depends on an abstraction instead of a bunch of low level modules, guys. So this was pretty similar to the example we did with OCP, just slightly different in the setup, but the principle is the same here, right? We want to depend on abstraction and make sure that we don't have a high level module depending on a bunch of low level modules. So that is really going to wrap it up for our examples with S.O.L.I.D architecture, guys. And if you guys want to continue your learning and see how this is applied in real life mobile applications, go ahead and check out the Swift Networking Masterclass. The link is in the description for that. And this just builds a cryptocurrency app with a full networking layer, guys, using all of the S.O.L.I.D architecture principles. So you can see how these principles are applied in building a real life mobile app with the Swift Networking Masterclass. That's available on the website. You go to courses, and you guys can either buy that as a one-time purchase, or you can become a member for less than a coffee a day and get unlimited access to everything on the site, guys. That includes all of the pro courses, all of these amazing app templates that we have for less than a coffee a day. So if you guys are serious about investing in your future as an iOS developer, make sure you check us out at stephencodes.com. We have so much awesome material there for such a low cost. So thanks for watching this one, guys. Hope you enjoyed it. We'll see you in the next one. Peace out.